Now we're going to look at taking a differential equation and we're going to solve it. And exactly what are we doing here is we are given that the rate or the slope of a particular equation is defined by this 2x divided by y, and we're going to try to go back and find the original equation. So we're trying to get to the goal where we're solving y equals something. So the separation of variables just means we're going to try to get everything with y in it on the left, including the dy, and everything on the right hand side that has a dx in it, and then we're going to just take the integral of both sides. So you can see that if we cross multiply here, if we cross multiply and get rid of this fraction, or both of these fractions actually, in this case we would have y times dy is equal to 2x dx. And then, since we have everything grouped in terms of y on the left and on x on the right, we can simply just take the integral of both sides. So doing that, we get that the integral is y squared over 2, and that's equal to what? 2x squared over 2 plus some constant. And notice we're just going to place the constant on one side of the equation because, if you have a constant on one side and another constant on the other side, if you add or subtract them, you're still going to come up with another constant. So we just resolve that by just writing the constant on one side. Typically we do it on the right hand side. So to solve for both sides, we would get, if we multiplied both sides by 2, that would get rid of this 2, and of course these two already cancel. If I multiply by 2, we would end up with y squared is equal to x squared plus c. And if I multiply by 2c, it's still a constant. And then I'm going to just take the square root of both sides. Take the square root of both sides, and we're going to get that y is equal to plus or minus square root of 2x squared plus our constant. Okay, let's take a look at another example here. And oh yeah, by the way, I didn't mention this. This is called the general solution, and it's a general solution because it can change based on what this value of c is. We don't have any other information about where this graph lies or what points are on the graph, so we just simply leave it with our constant in there, and they call that the general solution. So let's take a look at number 4, and you'll notice right away that there's no fraction here. In fact, the x term is missing altogether. So if we multiply by dx, we get, get rid of that highlighter. We get that dy is equal to 4y dx. Well, we need to get our y out of the right hand side, so I'll just divide both sides by y and both sides by y, and I'll end up with dy over y is equal to 4 dx. And then we can go ahead and integrate both sides, and I'll do that up here, and we get the fact that we get the natural log of y is equal to 4x plus a constant. Okay, so, and this is often overlooked, but it's the absolute value of y. When you take the integral there, the natural log always has to be positive there. So how are we going to get this y out of that natural log? Well, hopefully you remember that we're just going to raise both sides to the e power. And if we do that, you get cancellation here. When you take e and raise it to the natural log, it's going to simplify, and you get the absolute value of y is equal to e to the 4x plus c. And if you remember, if we look at e, it's always going to be a positive term, so we can drop the absolute value because it's always going to be positive, and we end up with, this is the graph of e to the x over here, whether it's e to the positive x or e to the negative x, it still is always going to remain above the x-axis, so it is always positive. So we have y is equal to e to the 4x plus c. Let me change colors and do a little side work over here. Let's say if we have x to the third power and we're multiplying it by x to the fifth, of course you would just look at that and say that's x to the eighth, but really it's the same thing as adding 3 plus 5, right? So we have a similar setup down here where we have e to the 4x plus c. So in order to get that c kind of separated from the 4x, I can rewrite it like this: e to the 4x times e to the c. And that may seem like a little thing, but e to the c, which has the constant in there, typically what we do is we just rewrite it. E to the c is still some arbitrary number that we're not sure what it is. So we write the fact that e to the c is equal to capital C, and that just tells us that we can pull this out in front, and typically we write that constant in front of the e term, and it would look like this. So hopefully this helps you, gives you a couple of examples of solving a differential equation by using the separation of variable techniques.